Hello everyone, I'm Dipendra Magaju, a recent graduate from UNESCO IHE Institute for Water Education at Delft, Netherlands. This is a short visual presentation of my MSc research work, which is the part of MSc curriculum here at IHE. My research is related with the development of a framework consisting hydrological and hydropower model to assess hydropower potential of the hydrologically data inexpensive basin. In order to assess the hydropower potential, we need to have two variables. First one is the design discharge, which can be determined from flow duration curve using hydrological model. And second is the head, which is the difference between intake and powerhouse elevation and can be obtained from topographic data using hydropower model. Now, explaining about the hydrological model, I have considered analytical stochastic model developed by Boter. For more detail about this particular model, I would like to request to go through the published papers regarding it. According to this model, probability distribution function of the flow at any point can be related with four climatic and topographic parameters. First one is the mean rainfall depth alpha, which can be obtained from precipitation data. Second one is the lambda, which is frequency of effective rainfall, and this can be obtained by using potential evapotranspiration and precipitation data. Third one is the recession exponent, which can be obtained by analyzing topographic data by using geomorphic recession flow model. The last parameter, which is coefficient of recession, can be related with previous three parameters. So once we have previous three parameters, it can be calculated easily. And after having all these parameters, probability distribution function and flow duration curve is plotted, and these are then validated at the gauging stations. Calculation of first two climate dependent parameters starts after the interpolation of point rainfall data into daily precipitation raster. In this research, I have considered inverse distance weightage method to interpolate point rainfall data into aerial precipitation raster. Once we have a daily precipitation raster, average precipitation of upstream catchment area at every point along the river is calculated. The black shaded box is the point in the river, and the area with the blue line is its catchment. So depending upon the value of this average precipitation, a Boolean raster storing either 1 or 0 is created at each daily time scale. Once this process is completed for entire time series, frequency of precipitation is then calculated as the ratio of sum of all Boolean rasters to the number of time series. This is then followed by the calculation of mean rainfall thickness as the ratio of cumulative average precipitation to the precipitation frequency. Now, in order to calculate the frequency of effective rainfall, dryness index is calculated using potential evapotranspiration and precipitation raster. Using this dryness index, runoff coefficient is calculated by using Budico's empirical water balance model. Then finally, effective rainfall frequency is calculated as a product of precipitation frequency and runoff coefficient. The remaining two parameters are calculated by using geomorphic recession flow model developed by Biswal and Marani. This model is based in an assumption that the origination of recession part of the flow hydrograph depends on the temporal variation of stream network after the precipitation event. So the input to this model is the river network as shown in figure, which is the combination of various individual river reaches which has to be separated based on their length. So at first the longest length is separated, and the process is continued until the entire reaches are separated. After this, two additional parameters has to be defined. First one is NL, which is the total number of reaches, whereas the second is ZL, which is the sum of length of each individual reach. After this, these parameters are plotted in logarithmic scale. We have already got the first point at initial stage. Now, in order to get additional plotting points, we have to shrink these river reaches, and the shrinkage is started from the shortest one. This process is continued until we have enough points to determine a linear equation representing this plot. This equation is basically a logarithmic transformation of recession equation, which means its slopes represent the exponent value. The typical plot of these two parameters looks like the one shown in the figure at the right. Now, once we have these three parameters, alpha, lambda, and exponent A, the last parameter can be calculated as a function of these three multiplied by certain constant. Next is the hydropower model, and the input to this model are discharge raster and DEM. Discharge raster consists of design discharge at every pixel along the river. In addition to this, it also requires few other parameters related with project length, capacity, and the cost. Now, in order to identify the project, first the individual reaches are separated in this case also. Then the intake of first project is placed at the most upstream pixel of that reach. Once this first intake is located, at every downstream pixel, river length from intake to that pixel is calculated, and this process is continued until we reach at the pixel where the river length exceeds the minimum threshold length. After this, specific cost, which is the ratio of base cost of the project to initial capacity, is calculated at every downstream pixel until we reach at the pixel where either power or length exceed the maximum threshold. Once we reach at this point, we stop over here, we look back and find the pixel where the specific cost is minimum. Now in this figure, we have minimum specific cost at pixel number 3. So we locate the powerhouse at this particular pixel corresponding to minimum specific cost. Then the intake of the second project is placed immediately at the downstream pixel of first powerhouse. This process is continued or repeated until the entire length of the reach is completed. Same process is repeated again in order to calculate the potential of the whole basin in other reaches also. So this is the basin where this framework was tested. It is known as West Rapti Basin with a catchment area of almost 6,400 square kilometers, located at the midwestern region of Nepal. The data used are topographic data, potential evapotranspiration data, precipitation data, discharge data, and few other data required for hydropower model. The precipitation data and the discharge data are observed data at the daily time scale, whereas the topographic data and potential evapotranspiration data are remotely sensed data. This is the result of the hydrological model, and from this figure we can see that the model is pretty able to capture the portion of flow duration curve corresponding to higher exceedance probability. Since this portion is more important to determine the design discharge of ROR hydropower project, so we decided to use this result, and we created a discharge raster storing a discharge value corresponding to 40% exceedance probability as an input to hydropower model. After creating a discharge raster using hydrological model, power potential assessment was done by using hydropower model. Altogether 79 projects with total capacity of 320 megawatt were identified in the basin. Various statistics were derived from identified projects, mainly related with the capacity, head, design discharge, specific cost, and so on. So this is a very brief summary about my master's thesis research. I have mentioned very few things over here because I wanted to make it very short. If you want to have more detail about it, then you can find my full thesis report in the official website of IHE Delft Institute for Water Education. I'll also try to post another video which will be about how to use this framework. It consists of few pieces of code scripted in Python, including the use of GIS. Meanwhile, thank you very much for your time. I'll be very happy to see your comments and suggestions. Thank you very much.